Hey everybody, it's Silversherm, and welcome back to the Blender Solar System. Last time we took a look at planet Venus, and now we're moving on to planet Earth. Earth, of course, is the third planet from the Sun and the only celestial body known to be able to sustain life. Now, because Earth has only been recently in human history considered a planet, it is the only planet not named after a deity. Planet, meaning wanderer, was the term used to describe the points of light that appeared to move across the sky, and of course, since we're on Earth, Earth didn't really fit that definition, but we as a species eventually discovered that Earth is quite a lot like those moving lights, so now it bears the title of planet as well. So the name Earth comes from various Old English words that all refer to the land in some form, but Earth is a personified goddess in various mythologies, like the Roman Terra and the Greek goddess Gaia. Now, usually the term terrestrial is used to refer to the Earth. There are also words like Terran, Tellurian, or earthly. And, of course, in fiction, you might see beings from Earth referred to as Earthlings. Now, with a diameter of over 12,500 kilometers, Earth is the largest terrestrial planet. It is, in fact, believed to be the largest rocky body in the solar system. The only larger objects are the Sun and the 4 gaseous planets. Now over here, if you look at the dimensions, you'll see that I have Earth a little wider than it is tall. That is due to an effect caused by its rotation, causing it to get squished a little, but on Earth it's not particularly noticeable. Earth is also the densest planet in the solar system, but that is partially due to gravitational compression. If you were to remove that, then Mercury would be the densest planet, based solely on the density of its materials. Looking at its surface, you can see about 70% of it is covered in water. Earth is the only known body in the solar system with liquid water on its surface. Now, Earth rotates on its axis once every 23 hours and 56 minutes. This is, of course, slightly less than your typical 24-hour day. That's because it is actually Earth's orbit that causes that day to get stretched the extra 4 minutes to 24 hours, give or take a few milliseconds. As you can see, Earth is tilted on its axis by about 23.5 degrees. This tilt is the cause for the Earth's seasons. When the northern hemisphere is tilted away from the sun, like is shown here, it is winter in the northern hemisphere and southern in the summer. And of course it changes as Earth orbits the sun. Now, before we move on to Earth's orbit, we have something else to talk about because Earth is our first instance of a planet with a natural satellite, which in this case is, of course, the Moon. The moon is Earth's only natural satellite, and from Earth it is the brightest object in the sky other than the sun. However, the moon's surface is actually pretty dark. It's just because of its closeness that it seems so bright, especially compared to the soul-sucking darkness of space. So like Earth, the moon's name comes from several Old English words that were derived from month, which is the unit of time measured by the motion of the moon. It's also occasionally called Luna, which is what the adjective lunar comes from. You might also hear Selenic, Selenian, or Cynthian, referring to the god Cynthia. Yeah, the Greek goddess Cynthia of the moon. Now, among other moons in the solar system, the moon is the 5th largest, but it is also the largest with respect to its planet. It has a diameter of around 3,500 kilometers, which is just over 1/4 of the Earth's diameter, and it is just slightly smaller than the planet Mercury. Now I'm going to center the view so we can take a look at the moon's orbit around the Earth. Now, I do not want to get into how much work it took to make the moon's orbit as realistic as possible. Actually, not just the moon's, all the orbits I made. I put in a lot of work making an elliptical orbit that is tilted with respect to the planet's orbital plane. I also got the values of the longitude of the ascending node, which is the angle between the first point of Aries I mentioned earlier and the point where the object travels north of the plane of reference, and another thing, the argument of periapsis, which is the angle of the ascending node to the point of the closest approach to the primary, which in this case is the Earth. But these values change over time, and as you can see, if I play it and speed up time a bit, yeah, the moon's orbit changes over time. Yeah, so that's just a lot of complication. I even made it speed up as it gets closer to the Earth. Yeah, it was a pretty complicated process, but let's just get into the moon's orbit. So the moon takes approximately 27.3 days to orbit the Earth. And the moon is also tidally locked to the Earth. That means its rotation period is exactly the same as its orbital period, and so it always shows the same face to the Earth. That face we always see is called the near side, and it is covered in dark spots called Maria. The other side, the far side, has considerably fewer dark spots, and we can't really see it from Earth at all. So we had to wait until spaceflight to see what that looked like. Now, I'm going to go ahead and throw in a camera here so I can show you all something. Okay, so here I have a camera that is set to always point towards the moon, and you can see that as time progresses, you can see the phases of the moon, which change based on the relative positions of the Earth, the moon, and the sun. And you can see that because of the moon's changing orbit, the moon appears to wobble slightly as seen from the Earth. Another thing I'd like to talk about is the Barycenter between the Earth and the moon. The Barycenter is essentially the center of gravity between two objects, and the moon is large enough compared to the Earth and far enough away that the Barycenter is considerably far away from the center of the Earth. So, as you can see, as the moon orbits the Earth also seems to wobble around that point. And now a few more things to show you. Because the moon's orbit is tilted, it is not always perfectly aligned with the Earth and the Sun during new moons and full moons. But there are occasionally times when it does line up perfectly, and those create solar and lunar eclipses. Now, if I set the time to represent the solar eclipse of August 21st, 2017, and make a few more adjustments, you can see the moon's shadow on the Earth. You can see the moon is over here. My makeshift sun is off in this direction, and it casts a shadow going right across North America. And now, for the other kind of eclipse, a lunar eclipse, this time the one of February 21st, 2008. And if I adjust this a bit, there we go. You can see the moon seems to disappear. That is because it is in the shadow of the Earth. Now, real lunar eclipses usually just make the moon look red because of the Earth's atmosphere. I wasn't able to quite replicate it in this, but if I make the Earth invisible and leave behind its atmosphere made using volume scattering and absorption, the moon does actually look red, but if I have the Earth there, it's just covered. But anyway, that's solar and lunar eclipses. So without further ado, let's take a look at Earth's orbit. So, back in the solar system, I have added in Earth's orbit. Now, Earth takes about 365.256 days to orbit the Sun. Now, that extra, approximately a quarter of the day, is why every 4 years we add an extra day to February as a leap year day. It's to keep the calendars up with Earth's orbit. I guess it's not perfect, but it's pretty much the best we can do. Now, as you can see from the side view, Earth's orbit is pretty much perfectly parallel with the XY plane. That is because Earth's orbit is what defines the ecliptic plane. And it's the plane which the other planets' orbits are typically measured to. There's nothing particularly special about Earth's orbital plane, but it's just, since we live on Earth, it's convenient to use it for measuring purposes. So Earth orbits the Sun from an average distance of about 150 million kilometers or 93 million miles, and this distance is called the astronomical unit. Now, as you can see, I have a camera parented to the Earth system. And I have the moon here too. So if I go into the camera view, rendered, I can set this camera to point towards the Sun. Now, just like before, I can go to that solar eclipse, and with a few adjustments, I can reach the point to where the moon passes in front of the Sun. And since the Sun is about 400 times larger than the moon, but about 400 times further away, the Sun and moon look almost the same size from Earth. Now, the moon here doesn't quite cover the Sun, but if I move the camera upwards, hang on. I can make it work. See the moon passing in front of the Sun. Now, if I zoom in on the camera, you can see that we're now kind of viewing it from the northern hemisphere, which is where that solar eclipse was visible anyway, so it works out. And now, a few more things I'd like to show. I believe approximately every 7 years, I believe it's less often than that, but whatever. Occasionally, Mercury will pass between the Earth and the Sun. The last time this happened was on November 11th, 2019. Now, if we see if we can... Okay, so there's Mercury. And here, we can see that little dot on the face of the Sun. Of course, Mercury is bigger than the Moon, but it's much further from the Earth, so it appears much smaller in the sky. And as Mercury can cross the face of the Sun, so does Venus. This happened on June 5th, 2012, so let's check it out. See if we can see Venus. Okay, it's over there, so move it back. Okay, and it seems to be kind of off. Hang on. Okay, yeah. The camera's not quite a ways above the Earth, so it's not perfect, but what are you gonna do? Now we can see a larger dot moving across the face of the Sun, and that, of course, is Venus. So that's it for planet Earth. Next time, the Blender solar system, we're going to continue on to the next planet. See you then.